Hello friends, welcome to Susan and John MathTube. In this video, we'll be learning two different types of problems. One will be verification type and the second one to find A inverse given A but using Cayley-Hamilton theorem. And the questions will be based on your past year's question papers. So you can note the first question. Verify Cayley-Hamilton theorem. I'll repeat. Verify Cayley-Hamilton theorem for the matrix. We have a 3 by 3 matrix and you know what is Cayley-Hamilton theorem. In the last video, we proved Cayley-Hamilton theorem, that is every square matrix satisfies its own characteristic equation. So the first thing we have to find is the characteristic equation. And you know there are two methods. One is the direct approach. You find determinant a minus lambda I and equate it to 0 and simplify till you get a cubic equation because we have a 3 by 3 matrix. And the second method which I am going to do here, that is you find the trace. What I mean by trace? The sum of leading diagonal elements, that will be 1 plus 1 plus 1, that's equal to 3. And S2, that means sum of the minors along the leading diagonal. So that will be 1 minus 1 minus 1 1 plus 1 3 1 1 plus 1 0 2 1. And that simplifies to 1 minus 1, that is 0, and then 1 minus 3, and finally 1 minus 0. So we get 2 minus 3, that is equal to minus 1. And for the last one, that is S3, the determinant of the matrix, I'll strongly recommend use a calculator. And the value is minus 9. So we have S1, S2 and S3. So the characteristic equation is lambda cube minus S1. The value of S1 is 3 and that gives me minus 3 lambda square. And S2 is minus 1. So this is going to be plus into minus, that's minus lambda, and finally plus 9 is equal to 0. Now look at the statement. Every square matrix satisfies its own characteristic equation. So we have to verify whether we can replace lambda with capital A. So you can write, we have to verify, or you can write according to Cayley-Hamilton theorem, a cube minus 3a square minus a plus 9 is equal to 0. Of course, this doesn't make sense, so I have to make it 9i. And this is exactly what you're going to verify. So, if you want to verify this, we need the identity matrix. And you know the identity matrix 1 0 0 0 1 0 0 0 1. And of course, this depends on the order of capital A. If A is a 2 by 2 matrix, then we will use 1 0 0 1. And if A is a 3 by 3 matrix, then we use I is equal to 1 0 0 0 1 0 0 0 1. And if it is fourth order, then the fourth order identity matrix, etc. etc. Now the next thing, that is capital A, and capital A of course is our question. Now we have to find A square. Okay, so A square is A into A, and that will be, we can copy A, that is 1 0 3 2 1 minus 1 1 minus 1 1 times 103 2 1 minus 1 1 minus 1 1. And I'm sure that you're very good in matrix multiplication. So just go ahead, multiply, or if you want you can use a calculator and find a square. And the answer is 4 minus 3 6 3 2 4 0 minus 2 5. So finally we have a square. Now take a look at this, the last one, a cube, and a cube is a square into a, or you can write a into a square. Okay, so let's go for a cube, and that is a square into a, and that will be 4 minus 3 6 3 2 4 0 minus 2 5 multiplied by the given matrix 1 0 3 2 1 minus 1 1 minus 1 1. If you want you can multiply, because it's like 4 minus 6, 4 minus 6 will be minus 2 plus 6, that is 4, etc., etc. 4 minus 9 21, 11 minus 2 11, 1 minus 7 7. Okay, now the verification part. So let's write LHS. So the LHS is a cube minus 3a square minus a plus 9i, and that is 4 minus 9 21. Just copy the matrix, 1 minus 7 7 minus 3a square. If you want you can multiply a square with 3 and put it over here, but I'm going to write 3 and our a square, and that is 4 minus 3 6 3 2 4 0 minus 2 5, and minus a 1 0 3 2 1 minus 1 1 minus 1 1 plus 9i. 9i I'm going to write directly, that will be 9 0 0 0 9 0 0 0 9, and that is equal to, of course I know the answer, it's a verification question and we proved Cayley-Hamilton theorem generally, so I'm going to get 0 0 0 for sure. But in case you're worried about your calculation, you can check it, 4 and then minus 12 and minus 1 and plus 9. So 4 minus 12, that will be minus 8 minus 1 minus 9, so that is 0. And next is minus 9 plus 9, that is 0. And the third element, 21 minus 18, that will be 3, and 3 minus 3 again 0. And second row, first element, so 11 minus 9, that is 2, 2 minus 2 0. Now minus 2 minus 6, that will be minus 8, and a minus 9 plus 9, that is 0. Same with the other elements. Okay, so we got the 0 matrix, and that is equal to RHS. So this is the first type, that is verification type. So we will do one more very simple problem. So please write, verify Cayley-Hamilton theorem for the matrix A is equal to 1, 2, 3, 4. So it's a 2 by 2 matrix, and I gave you this example so that you are familiar with characteristic equation of 2 by 2 matrices, because in all the previous videos we were worried about 3 by 3 matrices. Anyway, method 1, determinant A minus lambda I equal to 0, and that will be determinant 1 minus lambda 2, 3, 4 minus lambda equal to 0, and that gives me 1 minus lambda into 4 minus lambda minus 6 is equal to 0. Now I'll expand, so 4 minus lambda and then minus 4 lambda plus lambda square minus 6 is equal to 0. That is lambda square minus 5 lambda, and that will be minus 2 equal to 0. So we have the characteristic equation. Since this is a 2 by 2 matrix, since the given matrix is 2 by 2, the characteristic equation of course will be a quadratic equation, and determinant evaluation is very easy. So to be honest, you don't need a shortcut, but still if you're curious about the shortcut, let's go for it. So method 2, the shortcut method, and here S1 will be equal to the trace as usual. So 1 plus 4, that is 5. And S2 means the determinant, because there will be only S1 and S2, not S1, S2, S3 like the cubic case. And S2 will be equal to the determinant, and determinant is 4 minus 6, that is equal to minus 2. And the equation is lambda square minus S1 lambda plus S2 equal to 0. That gives me lambda square minus 5 lambda minus 2 equal to 0. Anyway, I prefer this method because we can write the answer even without writing S1 and S2, because we can calculate those things in our mind. So this is really fast, and if you don't want to by heart this formula, you can go for the determinant method. Anyway, we have the characteristic equation. So what exactly are we supposed to verify? Yeah, we have to verify that every square matrix, in this case capital A, satisfies its own characteristic equation. That is, we have to verify that A square minus 5 into A minus 2, of course doesn't make sense, so 2i equal to 0. Remember, whenever you convert a polynomial equation into a matrix equation, don't forget to add I. And in this case, I will be equal to 1, 0, 0, 1. And of course, you know what is capital A, that is a given question, that's our 1, 2, 3, 4. So all we have to do is we have to evaluate A square. So let's go for A square, that is A into A, that will be 1, 2, 3, 4 times 1, 2, 3, 4. If you want, you can use a calculator or do it directly. So 1 into 1, that is 1, plus 2 into 3, 6, then 2 plus 8, and now the second row, so 3 plus 12 and 6 plus 16, and that is equal to 1 plus 6, 7, and 10, 15 and 22. Now let's write LHS. So LHS equal to A square minus 5 into A minus 2 into I, and that is equal to 7, 10, 15, 22 minus 5 into 1, 2, 3, 4 and 2i. 2i is 2, 0, 0, 2. Now let's simplify. So 7 and this 5 goes inside. 7 minus 5, that is 2. 2 minus 2, as expected, 0. Now 10 minus 10, and that's 0. 15 minus 15, and 22 minus 20, that is 2, and 2 minus 2, 0. So as we expected, it's equal to 0, so that will be equal to RHS, and that's it. So we have verified Cayley-Hamilton theorem, and let's move on to the next type of problem. Let's use the same question so we can reduce the steps. So please write the question. Consider the matrix. Using Cayley-Hamilton theorem, find its inverse. You learned Martin's method in class 11 to find matrix inverse. So this is another method that is called Cayley-Hamilton theorem method. Okay, so what we do is, as usual, we find the characteristic equation. And this is the same problem which we did earlier. So I'm going to reduce the step. So please write the characteristic equation is, I think you have the answer, lambda cube minus 3 lambda square minus lambda plus 9 is equal to 0. So this is our characteristic equation. Now we will write, according to Cayley-Hamilton theorem, every square matrix satisfies its own characteristic equation. Therefore, we have a cube minus 3a square minus a plus 9i is equal to 0. Okay, now in the next step, what we do is, we multiply throughout by A inverse. And always remember, A inverse multiplied by A gives identity matrix. So if you multiply A inverse with A square, what happens is, it becomes A inverse into A into A, because A square is A into A. Now matrix multiplication is associative, so this will become capital I into A. But identity into A is A. Okay, so when you multiply A inverse with A square, you end up with A. And using similar logic, if you multiply A inverse and A cube, you're going to end up with A square. And if you multiply any number or any scalar into A inverse, you get the same thing. So the next thing to do is, we have to multiply throughout by A inverse. So tell me, what is A inverse into A cube? Yeah, exactly. That is A square minus. Now what happens over here? Yeah, we get 3 into A minus, okay, this will get simplified and we get identity matrix. And the next one, 9 into A inverse into I, that will be 9A inverse is equal to 0. Now, what are we trying to find? Read the question. Yeah, the matrix inverse. That means we are going to write 9A inverse, or we are going to keep this on the left side, and we will take all the other quantities to the right. So we get I plus 3A minus A square, and that gives me 9A inverse equal to, identity is 1 0 0 0 1 0 0 0 1 plus 3 times A. That means we have A, you multiply this throughout by 3, that will be 3 0 9, 6 3 minus 3, and 3 minus 3 3. Let's copy that. So plus 3 0 9, and then 6 3 minus 3, and 3 minus 3 3, and A square we already calculated earlier. You can check that answer, or you can just rewind the video. Anyway, a square is 4 minus 3, 6, 3, 2, 4, and 0 minus 2, 5. So that gives me 9a inverse is equal to, let's calculate. So 1 plus 3, that is 4, 4 minus 4, 0, and then 0 plus 0, and then plus 3, and we have 0 plus 9, and 9 minus 6, that is another 3, and the second row 6 minus 3, again 3, and then 1 plus 3, 4, and 4 minus 2, 2, and minus 3 minus 4, that is minus 7, and 0 plus 3, 3, 3 minus 0, 3, and 0 minus 3 minus 3 plus 2, that is minus 1, and the last one 1 plus 3, 4, 4 minus 5, that is minus 1. So that's it. So we are going to have A inverse is equal to 1 by 9 times 0, 3, 3, 3, 2, minus 7, 3, minus 1, minus 1. That's it. So we learned two different types of problem which they might ask for your exam. One is verification of Cayley-Hamilton theorem, and the second one, how to find matrix inverses using Cayley-Hamilton theorem. Anyway, I'm going to stop the video right now. Soon I'll be back with another video in which we'll discuss the last topic in matrix, that is diagonalization. And then there'll be one video and that'll be related to determinants. And so till then, bye.